Okay, where is it? Alignment. Source. Okay, alignment. We start alignment. Ya, lain ramai tak jauh ni 11. Okay, alright. Kita slowly kita get started slowly sebelum yang lain join. Kau dengar lagi ABC tu abaikan ya. Okay. Selingan ABC tu. Kau dengar lagu Frozen ke abaikan je. Okay, can you see the slides? Okay, kan nampak?
Nampak tak? Saya nampak.
Alright, thank you. Okay, so let's continue from our previous class. So we stopped at alignment, and we were discussing about the 8 steps in lithography process, okay, which is expanded from CED, right? Coating, exposure, and development, and then we continue to discuss on the exposure system and then alignment. We stop at alignment, and alignment is one of the main factors or main process parameters that needs to be measured or characterized after the CED process. Okay, so after the CED, you have to do the very first thing is visual inspection or VI, or in this lecture we say develop inspection, right? Develop inspection, and essentially it is a visual inspection. So that is one. The next thing that has to be measured is CD, right? Critical dimension, which is the line width of the resist that we have printed during the CED process. And then another factor that has to be measured is alignment. Okay, alignment, because we discussed before, when you want to print the current layer on the previous layers, you want to make sure that you need to make sure that the current layer is perfectly aligned to the previous layers. Okay, in this case, we stopped at this slide last time, where you can see where perfect overlay is demonstrated on the left. ABC, yeah. Okay, perfect overlay is demonstrated on the left. So you can see that the box, in this case, the feature or the box, is well positioned, is well printed inside the area that we intend to print. Okay, and on the other side, you can see on the right hand side where we have a shift in overlay, ataupun shift in registration. So registration and overlay is actually referring to the very same thing, but the detailed definition is slightly different. Tapi the whole idea is you want to align your features accurately in the zone, okay, or in the area that you're supposed to print. So in this case, on the right, you can see that there's a shift in overlay. So if you're referring to the gray box, for example, so you can see that the box is, the feature is printed with a bit of shift plus X to the right, and then with negative Y, for example, okay, slightly below the intended area. Okay, maknanya dia shifted ke kanan dan ke bawah sikit. Okay, so that's the shift in overlay, and this kind of shift depends on the target, okay, the target specification that you want to print. Okay, for example, so if we are working on the latest state-of-the-art technology nodes, for example, then the shift in registration, the tolerance will be very, very small. Okay, So we discussed this before, and we discussed about the uh, alignment marks. Okay, so where before you start your exposure process in the scanner needs to find the alignment mark before the printing can be done, before the scan and print, okay, and expose. So selagi dia tak jumpa alignment mark tu, it won't start the process. Instead, it will raise an alarm to say that, for example, alignment mark problem or something. So normally, in litho case, we normally see this global alignment problem. Global alignment means before the scanner starts printing, so it couldn't find the alignment mark for some reason, okay? Whether it's not so clear or the position is a bit off, or there's some disruption on the surface of the wafer, and tons of different root causes, okay? So, but it will give you the alignment mark error, GA error lah. Normally kalau dekat error tu dia akan pop up GA error lah dekat display. So bila ada GA error ni, normally what the operators need to do is they have to respond. They have to go back to the system and see where's the problem, okay, that has caused the GA error, and then fix that. Sometimes it's just a single press of a button, and then it will try to research for the alignment mark, and then it's okay. Okay, kadang-kadang just a push of a button, yeah, then it can fix. You can research, you can revisit the location, and once found, then the exposure will start. Okay, so if the alignment mark couldn't be found, then the exposure will not start. So that means your process, your exposure process will not start. They can start as to and give some errors. Okay, so after the exposure, there's a process that we call PEB, or post-exposure bake. So essentially what we do is we bake the pattern that we've printed. So remember at this phase, so let's recall your 8 steps. So say if you have silicon here, then you'll probably have oxide in between. Then say this is your resist. PR, photoresist. Okay, so at this stage, you still have your resist layer intact. So it's not yet removed because it's not being developed yet in developer stage. Okay, but at this point, you already have your patterns exposed. For example, if say this is positive PR or positive photoresist, okay, katalah in this case we have exposed these shaded regions. Yeah. Selingan siang Okay, so for example, yeah. TV ya, nak TV pula. Sini. Sedang. Sekejap. Sekejap, give me 5 seconds. Sorry. Okay. All right. At this point, we have exposed the resist, but we haven't developed the resist. So, basically dalam resist tu kita dah ada area yang dah ada reaction. Okay, if you revisit the mechanism last time, let's recall. For a positive resist, these areas are exposed. So what do we expect to happen in these areas once it goes through the development stage? Anyone?
Harden.
Positive resist, huh? Positive resist. What do you expect? These areas, hardened or soluble? Soluble, right? Soluble, huh? Positive resist, exposed, soluble, okay? So you can you have to understand, right? That's the very basic one. So if you're clear with that, then the rest will be okay. So expose, positive resist, expose soluble, negative resist, expose hardened. Okay. So in this case, we expect the shaded regions to be soluble later on. Okay. Sekarang not yet, sebab kita baru PEB ya. If you revisit back the 8 steps, so PEB comes before development, right? CED. Okay. Sekarang baru step E. Okay. So then, even though it's not yet removed, the regions are already having reaction. Okay, reaction maknanya upon exposure, we have induced reaction between the light and the resist. And once it goes through the development stage, these shaded regions will be removed. Tapi at this stage, when you go through the PEV process, what will happen is this PEB will chemically amplify the DUV resist to catalyze critical chemical reaction. It will further enhance the reaction of the photoresist. Okay, dalam photoresist dia akan further enhance the reaction. Okay. Then when we talk about the resist, there are a few types of resist. For example, if you talk about resist that is used on I-line system, we normally call it as DNQ resist, DNQ Novolac. So for DUV resist, we normally call it as CA resist, chemically amplified resist. So for this particular example, we're talking about this chemically amplified or CA resist. Okay, so they can trigger reaction in during the PEB step. So PEB is also required for conventional I-line resist to reduce standing wave and improve addition. So we're going to come to this standing wave issue after we talk about the development stage. Okay, so typical PEB temperature is between 100 to 110 degrees C on a hot plate, and then it's done immediately after exposure step. Okay. Now the wafer goes through development. Remember CED. Now we are at D. Now we want to remove this shaded region. Okay, kita remove this shaded region. Oh, sorry, shouldn't be. So do next page. Okay, let's go through the details first. Soluble areas of photoresist are dissolved. Soluble are dissolved by the alkaline solution. In this case, we use TMAH, tetramethyl ammonium hydroxide, alkaline solution. So if you talk about the positive resist, like on the previous page, silicon oxide, okay, katalah shaded region ni yang kita dah remove tadi. You exposed, just now we expose, and then it becomes soluble, and then these are the photoresist that remains. And yang shaded region tadi, if you go back to the previous slide, the shaded regions are now gone because they are now soluble in the resist, in the developer stage. Okay, so this is where you physically produce the patterns. Okay, if you look at the scanner exposure stage, dia baru induce reaction dalam photoresist, tapi kita tak remove lagi, right? So that means you don't have your patterns printed yet. Instead, you still have the resist covering the whole surface, but some regions have gone through or are going through the intended reactions, but waiting to be removed in the next step. And in this step, the exposed areas are removed. So if you are working on negative resist, for example, then the shaded areas in this case will be maintained on the surface, okay? Because they harden due to cross polymerization of the polymer. Right, when you do the CED process and when you develop your patterns, there will be few problems related to the pattern qualities. Okay, so let's look at this. This is the silicon substrate, and then just imagine you ada oxide atau maybe tak ada oxide pun in some cases, just to demonstrate. So you may have a couple of you may have few you may have few qualities of the resist after the CD. For example, if you underdevelop, maknanya tak cukup develop lah, tak cukup develop, then you will see your patterns to be like that. Okay. Kenapa kita punya underdeveloped? Because you haven't removed. You want something like this, but you still have this resist on the side of the pattern. So we call that underdeveloped. Okay, maknanya resist tu ada lagi kat tepi eh. Sepatutnya kita potong ni cantik lah. It is not perfectly square or vertical, but it's going to be a bit, dia akan jadi positive profile. Positive profile means dia akan kembang sikit kat bawah. So that's how normally what we get. But we don't want it to be so positive. So positive ni dia terlalu trapezium lah. Kita nak dia as square as possible. So that's the intended feature. Right, but due to certain limitations in the optics, in the material interaction with the light, we cannot have such a perfect structure. So if you do incomplete development, then you'll probably have resist left on the floor as well, on the silicon ataupun on the oxide. Okay, incomplete develop. So these two are bad, of course, because they are not as desired. So if you correctly develop the resist after the CED, then this is what you're going to have. So you can see that you have a little bit positive profile, so it's not perfectly vertical. Okay, so kita tak nak dia too positive like that. This is bad. And on the other hand, we don't want it to be like that as well. Negative dia masuk dalam kan. So that's possible as well. Okay, kita nak, ideally we want it to be perfectly vertical, but it just won't happen. You're going to have a little bit of positive profile on the side, so dia akan buka sikit lah. So then severely overdeveloped, you can also overdevelop. Okay, then you can see, for example, if your intended CD is line width, remember, say if your intended CD is 100 nanometer, so kalau itu lebih developed, that's also possible. So you'll probably be left with 60 nano perhaps. Okay, so something must be wrong with your process somewhere, somehow. Okay, perhaps it's due to the dosage during the exposure, or some misalignment, or perhaps your developer recipe is too long. Okay, it's too long, then you overdevelop. Okay, masih boleh juga. So this is the only correct one, correctly developed. Right? Yang lain semua tak betul. Yang lain semua is considered as a problem lah. Okay. So if you got those three conditions, underdeveloped, incomplete developed, severe overdeveloped, what you have to do at this stage is just to send the wafers for rework. Okay, remember what is rework? We discussed in the last class. What is rework? Let's recall a little bit. What do you work? Anyone? You can write down, you can unmute yourself. Saya settle online.
Dia baiki doktor.
Macam mana baiki?
Maksudnya kalau salah, maksudnya nanti dia apply balik coating, apply balik photoresist, lepas tu buat balik kan doktor? Kan?
Yes. Rework means you strip off the resist. Okay? So that means CED tu you dah print, you dah dapat feature pun. So kita hantar kat proses dekat next department, etching. It will go through etching process. Kita akan belajar in the next lecture, etching lecture. It will remove the resist yang ada atas wafer tu. Current layer will be removed. So then the wafers will be sent back to input of lithography process. Then it will need to go through the very same CED process so that we can generate the right profiles. Okay, so that is rework. So we only have this privilege in lithography, but not in other processes dalam wafer fab. Okay. So remember, you can rework after litho, but you cannot rework. You cannot rework after etch. So kalau you dah etch, then the wafers need to be scrapped. Tapi kalau kalau after lithography, kalau you ada this kind of problem, you don't have to scrap just yet, unless ada certain other problems. But if this is the problem, then you don't have to scrap. Okay, scrap is the last thing you want to do. It means the whole thing is gone. Wafer tak boleh guna dah. Kalau rework, you can just strip off the resist. Mana resist dah tak ada, you go send it back to start lithography. Then you can redo the CED, hoping that you're going to get the right features. Right, development stage still. What it does is it removes the exposed area for the positive resist and leave the exposed area for the negative resist. Okay. So in this case, cuba tengok gambar ni. So this case, in this picture, the resist is positive or negative. If you look at the description, an exposed positive resist on the side. Jawapan pun ada, positif lah kan. So unexposed on the side, that's why it remains, and then exposed in the center. Okay, resist exposed to light dissolve in the developed chemical, so it's positive, right? So there are few parameters that are important in this stage. In the developer stage, temperature, time, volume of the alkaline solution, normality, rinse, exhaust flow, wafer chart. Okay, dia punya modul macam kotak yang saya tunjuk hari tu, yang ada pintu tu. But then it runs the developer process. So how it runs, this is the details of the recipe, but not entirely the whole thing, because a typical developer recipe contains, I think, 10 steps or so. Maknanya dalam recipe tu ada step 1, belum spin. Step 2, start spinning at certain RPM. Step 3, spinning with, ataupun belum spin. I couldn't recall exactly 10 years ago. You dispense the developer, TMAH, and then start spinning at low speed and stuff like that, right? So the last time I handled this machine was in 2009, before resign. So that's like 11 years ago. We don't recall the recipe. Okay, so paddle dispense. Paddle dispense here means kita dispense apa developer recipe first, but you don't do anything yet. You just paddling, kumpul solution, let it let the features to be deep in the in the paddle. Jadi kita biar dia kumpul, and then you spin off excess developer after the paddling. Yep. Just ya. Ya. Oh, mama pula. Ya. Tolong kau lepas. Jangan. Ya. Give me 1 minute. Ya. Oh, tak ada bekerja. Okay, dah. Boleh? Nak. Buat nangis pula dia. Yeah, 1 minute, please. Sorry. Okay, I'll just continue. Dia nak tidur, saya tengah ribut sekejap. Okay, spin off the excess developer, and then the moment you have you spin off that means your removal of the photoresist is completed, and then you have to rinse using DI water. So remember the DI water, you have to have a resistivity of around of around 18 mega ohm. It's not normal water, okay? So it's called DI water or deionized water. Deionized. Deionized. Water, okay? Then so after the rinsing process, we can spin dry or remove the remaining DI water from the step. Okay, then we move on to hard bake, which is the last step. Okay, so hard bake means you bake the features that you have developed. Okay, so evaporate the remaining solvent, in this case solvent from the developer stages now. So the goal is to improve resist to wafer addition. So that means features yang kita dah print tu kita nak make sure that they are strong on the silicon. So that's why you have to perform hard bake. So normally the hard bake is conducted at higher temperature, so in the range of 120 to 140 degrees C. So if you recall and you compare to soft bake is typically carried out at 90 to 100 degrees C, and this one is like 20 degree to 30 degrees higher. Okay. So some characteristics of the hard bake process is done after the development process. It evaporates residual solvent from the resist and from the developer stage. It helps to harden the patterns, improve addition of this pattern, this PR photoresist. You still have to do something to make sure that the patterns are strong, okay, on the silicon wafer. Prepares resist for subsequent processing, okay, higher temperature than soft bake, but not to point where resist softens and flows. So dia tak boleh exceed certain temperature so that you don't damage the quality of the resist. Okay. Soften the resist flow at high temperature. Okay, so this is some examples of the resist that could be printed. Tapi kita dah cover tadi yang okay and not okay. Right. Right, so the last step is develop inspect, step number 8. If you recall the whole 8 steps, okay? The whole 8 steps is develop, inspect, and then as we discussed last time, the role of this step is to find defects, okay? Find defects. So you want to make sure that the wafers are clear of defects. So prevent scraps. So for example, if you have certain defects that exceed certain counts, and those defects are killer defects, so the wafers may end up being scrapped, okay, in some cases. For example, just let's discuss one example. Kalau during this develop inspect, then suddenly you found, so this is your wafer. This is your wafer, this is the notch. Then you have got your patterns printed already on the wafer, and then you found a deep scratch, for example, a deep scratch. Okay, a deep scratch is the defect suddenly found on the wafer after CED process. So do we have to send the wafers for rework, or do we have to scrap the wafers? Any guess? Do you think you have to scrap or rework?
Scratch tu dekat photoresist ke dekat wafer dah tu?
You can see a scratch in the resist, and it's a deep scratch.
Oh. rework lah. Kalau photoresist kita rework.
Okay, photoresist rework. What if the scratch goes deeper than the resist?
Then scrap lah kot. Memang kena buang.
Right, so that means you have to characterize the scratch, okay? So for example, kalau you nampak a very clear deep scratch, then you have to know the depth of the scratch in this case. So does it exceed the depth of the resist or just within the resist? Within the resist, and what you have to do is you have to try to send the wafers for rework, and then after the rework, you have to send the wafers to VI again, visual inspection one more time, to make sure that the scratch is no longer there. But if the scratch is already there, ataupun dia tak perasan sebelum CED, ataupun it's still there but introduced somewhere within the CED process, then most likely the wafers need to be scrapped. Okay, so it really depends on the troubleshooting. Maksudnya waktu ni tak ada, there is no single guideline that says the wafers need to be scrapped or just rework. It really depends on the nature of the defects. Okay, kalau you boleh strip off the resist and the scratch is no longer there, so that means we can just rework and redo the CED. Then kalau katalah you found that the scratch is there and you send the wafers for rework, and then after the rework you do the VI, visual inspection, and the scratch is no longer there, done. Then you resend the wafers for CED. And then after CED, last step kita buat VI balik kan, visual inspection. Bila you buat visual inspection after the second CED, you still found a scratch at the same point, the same location. What will you do?
Scrap lah.
Kenapa nak scrap?
Sebab ada juga dia punya scratch tu kan.
Any other guesses?
Sistem.
Sebab
Yap. Macam mana?
Sistem tu yang problem. The CED process.
System. Okay, CED problem. Okay, then what do you think you will do? Katalah you process engineer ataupun equipment engineer, kita just discuss the actual situation beyond the process. So what will you do?
Maksudnya kita kena inspect equipment lah pula. Bukan setakat wafer saja.
Right, good idea. Not only wafers, but also inspect the system, the whole CED system, that to find the potential location that could generate the scratch. Okay, so mungkin robot arm, mungkin anything that's moving or the positioning. Okay, so typically kalau case-case macam ni so proses tu akan shut down and equipment will be shut down as well, right? So kalau scratch tu introduced by the equipment, or at least we think it is introduced by the equipment, then we have to shut down the whole equipment CED. Then kita perlu run test wafers with some coating on, just like the actual CED process, tapi on test wafers, not on production wafers. Test wafer ni you can use for any test you want to do, to troubleshoot. Kita akan sentiasa ada test wafers dalam fab untuk you run test for whatever reason, with coating, without coating, just handling, whatever. And you can do thousands of different things on test wafers. So in this case, you might have to simulate the process on test wafers and try to see the movement during the movement of the robots, or any friction or any unusual symptoms during the run. Bila you run test wafer and you down equipment, you can actually open the equipment. Maksudnya equipment kita tengok sebelum ni nampak tutup semua kan. So normally ni equipment engineering sikit bila you run mass production, tiba-tiba you buka pintu, so it will stop the process immediately because there is an interlock. Okay, interlock tu it's supposed to be locked lah, the mechanism that is there to protect the wafers, the equipment and so on. So kalau you buka pintu sikit dia akan trigger alarm, dia akan trigger sensor, then dia akan cakap interlock error. Okay, my process akan stop immediately and things will go into a bad way lah. Maksudnya you stop something ataupun introduce some delay in between certain recipe, so then the whole wafers yang tengah run tu will be affected. Tapi kalau you run test wafers, during troubleshooting, you can actually disable the interlock. Okay, ni more on equipment side lah kalau you nak buat kerja equipment macam ni. Can disable the interlock, you can open all the doors, remove all the doors, then run the very same process untuk you tengok dekat-dekat macam mana proses tu, actually running. Ya. Oh, okay. Macam mana proses tu actually running, and you can then identify if there is any problem with the automation, robotic, and other potential problems. Okay, then only you know what to decide whether you're gonna fix anything. So most possibly kalau this problem persists during the CED, during the CED, then maybe robot arm tu ada problem lah. Usually, if say you find any problems on the robot arm during the CE process, you might have to reteach the robot arm. Okay, so waktu ni you punya programming punya skill akan jadi very important. It's not that you have to write the script is already there, but you have to make sure that you use the script accordingly to teach the robot ataupun reteach the robot. So this is the normal troubleshooting procedure that you have to do. Kalau ada robot problem, then you have to reteach the robot. Dia punya X, Y, Z, theta, you have to redo everything. Okay, so you have to move it slowly and see whether it's moving, putting the wafers in the correct way, or ada friction ke ataupun ada theta adjustment. So there will be some problems. Well, last time we used to have some problems on the hot plate where the robot is positioning the wafer not exactly in the region. Okay, so dia akan ada robot tu ada shift sikit for some reason, we don't know why. The shift, so bila shift, if you recall last time we talk about hot plate punya tu, dia ada sensor and dia ada placement tu kan, dia ada pin keliling tu. So then the wafers are slanted on the hot plate. Dia tak duduk exactly like that, but it sits like that because ada pin kat ujung. So bila robot letak sengit, dia akan duduk sengit, dan you punya baking will be one-sided. Okay, so you akan bake sengit lah kiranya. Bila you bake sengit dalam wafer tu, setelah ni you punya wafer, then you're gonna bake one side at higher temperature because it sits closer to the plate, for example, in this case. Then on the side that is slightly slanted, it's not baked properly. So you introduce the right baking, hard bake ke, soft bake ke, PEB ke. Then bila you buat measurement later on, overlay or CD or VI, you'll probably see something one-sided. Okay, maybe CD you can see it's on target on one side, but it's off out of spec on the other side. And then these are among the real things that you have to understand. You have to appreciate. You can only detect the problem while doing the measurement, but then the problem is not due to the process, but it's due to the equipment. Okay, so this is one of the cases that is possible. CD had a problem on one side, but it's always one-sided. One side okay, but the other 50% of the wafer is not okay, out of spec, out of control. Tapi it's not in the recipe itself. Bila you buat inspection, test wafer running, rupa-rupanya hot plate slanted. Dia punya wafer slanted on the hot plate due to robot arm punya placement. But why robot arm punya placement macam tu? You don't know. Then you have to, as an equipment engineer, you have to go and check. So have you learned anything on 5 whys analysis? Pernah dengar tak 5 whys? 5 why?
Tak.
Pernah? Okay, this is very useful bila you masuk dalam any work lah, ataupun especially engineering work, dalam fab ke, backend, I don't know why. I don't know where, but it's going to be very useful. For example, let me teach you. 5 why essentially means you kena tanya le why 5 kali. This is very useful lah. Nanti you nak interview tak ada dalam course ni, saya ajar sebab based on experience. In 3 je, tapi you have to go 5 times. 5. For example, so let's pick one issue. For example, bila kita measure CD, line width of the features after CAD, then the symptom is, what we see is the CD is out of spec on the lower side. Okay, and it's always one-sided. Kalau you measure the whole wafer, then one side is okay and the other side is not okay. Maybe on the lower side, for example. Then your question is why? Kenapa CD macam tu? Okay. Then you start digging down. You start digging the problem lah, digging for the root cause. Then you start suspecting. Okay, you start suspect maybe somewhere it's one-sided. Then you buat troubleshooting, you find that the hot plate, the wafer is slanted on the hot plate. Then the second question is why is it slanted on the hot plate? Okay. Bila you masuk dalam operation, dalam industri, the troubleshooting will be very structured. Dia tak ada room for you to wander around troubleshooting, and there's always a structured kind of troubleshooting. Kenapa CD problem? Sebab wafer slanted on hot plate. Kenapa wafer slanted on hot plate? Because robot arm doesn't place it correctly. Kenapa? So, okay, what was the third question then? Let's drill these 5 whys. First why is kenapa why the CD shows problem ataupun out of spec. Why the CD is out of spec? Then the finding is the robot arm, the wafer is slanted. The second why is why the wafer is slanted. Then the finding is the robot arm places the wafers incorrectly. So what would be the third why? What is the third why yang you would be asking as an engineer? Anyone? Okay, yeah.
Apa salah coding robot arm tu?
Okay, any other salah coding robot arm? Tadi finding kita robot arm salah tak ataupun dia tak accurately placed. Any other suggestion for the third question? Anyone? Any different question for the third one?
Why robot arm not correctly placed?
Soalan kedua apa? Dan okay, why robot arm not correctly placed? Okay, katalah kita jumpa, okay, if that's the question, kenapa, why did the robot arm did not place the wafers correctly? Maybe your finding is, I've done this one a few times last time. Sometimes the X is off. Sometimes X is this way. Nak tak wafer kan? Kita dah tengok video dalam e-learn tu. Say if this is your Y, robot arm macam tu kan pinset. If this is your Y, if this is your X, sometimes this is your theta. Theta tu dia punya angle. Sometimes the theta is off. Ataupun X off. Sometimes Y off. Sometimes many off. Ada X, Y, theta semua off. So dah ada troubleshooting punya flow. So say you found that the theta is off. So what would be your fourth question? Any idea?
Inspect robot arm tu.
Okay, inspect robot arm is the action, but your fourth question, you've just found that your theta is off. What would be your next question? Remember, your question has to be based on your previous finding.
Why the theta is off?
Yes, why the theta is off? It's very straightforward, right? So engineering troubleshooting is very straightforward. You sort of repeat what you found, but it helps you. So that's why I told you it's a very structured kind of troubleshooting. Okay. CD is our spec. Why is it so? Because robot arm tak correctly. Why is it so? Then robot arm punya theta is off. Why is it so? Macam why is it so lah. Dia nak jawab tu, tapi to be more accurate, why theta is off? Then you start opening the doors and running the robot arm punya on test wafer and see how much theta is off, why is it off, what could make it to be, what could lead the theta to be off? Is it some friction or movement or the belting? Okay, theta ni robot arm dia pakai belt macam-macam kereta pakai belt So kadang-kadang belt dia dah haus ke ataupun torn ke ataupun for some reason it's premature damage ke, then it will go back to the whole configuration around the robot arms. Okay, dia punya screw longgar, kadang-kadang ada screw longgar, technician buat PM tak screw balik properly. So thousands of different potential root causes. Okay, So bila you ada problem dalam engineering, it's very useful for you to understand these 5 whys. Why is it so? Then you dapat result. Oh, this probably due to why is it so? Then bila you go why is it so, you can solve the problem is CD is out of spec. Then you jumpa robot arm placement is not correct. Then you jumpa the exactly is due to the theta. Then you jumpa exactly due to the belting. And then you jumpa belting house. And then there's no PM. For example, or PM is skipped due to capacity too much capacity to run dan tak dapat PM time, then therefore you cannot replace the belting, therefore the theta is off, therefore the robot arm incorrectly placed the wafer, therefore the CD is off, therefore the wafer is slanted, therefore the CD is off, therefore you have a problem. So nampak you reverse balik kan? Can you see it now? Can you see the sequence of the 5Y kalau you reverse balik? Can you see? Is it clear to some extent? Okay, yeah? So these are among the things that I want you to understand on top of the current content. Content ni kalau betul-betul you tengok kat YouTube and ni you can understand to some extent. Tapi experience you cannot. You have to really know the thing. Okay. So banyak lagi benda yang saya akan ajar you along the way. These 5 whys is only one. You can also find FMEA, for example, failure mode and effect analysis. This will be useful as well. You can also find 8D, 8 disciplinary report. Okay, kalau ada problem tu, daripada you identify the problem, potential root cause, corrective action that you have done, preventive action, then many things. There are 8D, 8D thing, D1, D2, D3 sampai D8. So every problem yang you ada dalam wafer fab, you kena ada 8D report. Maksudnya engineer in charge, either it's equipment problem or process problem. The very next day, you have to present your problem in the form of 8D. Okay, nanti you explore what is 8D. It's going to be very useful if you look for a job in fabs or in the back end. Most of the companies pakai ni 8D, FMEA, 5 whys. Kalau you tengok dekat job description, dekat internship ataupun fresh engineer for example, then you will find, I bet you will find all this. Okay, sikit atau banyak ya. SPC, 8D, FMEA, 7QC tools, 5 whys analysis, fishbone diagram, all those stuff. Semua tu troubleshooting tools that can help you to do your job better, okay, as an engineer. So banyak lagi problem yang we can discuss later on. So let's just rework. Let me finish with this rework, and then we stop for like 10 minutes before we continue with the second session of the second part in lithography. So let's recap. HMDS, we did it for priming, and then photoresist coating, and then we performed soft baking in order to harden the photoresist, drive off solvent, and then we aligned before we expose. Remember the alignment mark and all the stuff, and then you expose your patterns as what you got on your mask or on your reticle, and then PEB to strengthen the features that you've exposed, to drive off the to induce reaction as well in the DUV resist, for example. And then you develop using TIMA to develop the features, to physically have the features, and you perform hard bake to drive off the solvent from the developing stage, and then you want to make the features stronger, and then we go to VI or develop inspect. Okay, so if your wafers have some problem that can be reworked, then they will go through this route. Okay, rejected but still can be saved. That's why we call it rework. Kita buat semula. So you're going to send the wafers to etching process. Pakai plasma, kita akan belajar this one in more detail in etching. Kita panggil etching etching. Yang satu lagi yang main process etching. Okay. But the whole thing, the whole idea is removal of material but through different techniques. Etching ni dia pakai O2 plasma. Plasma, oxygen, based on oxygen, kita create plasma. Then that will attack the resist that we want to remove with some accuracy. Okay, so they can remove the resist, and then the wafer will be sent back to HMDS dan masuk balik CD. Right? So if the VI pass, then the wafers will be going to the next step, either etching or implant, depending on the process flow. Okay. Process flow ni kita define since day one. Apa jadi kat wafers daripada the start sampai from day one sampailah dia habis bulan ketiga, bulan kedua. Okay, depending on the complexity of the technology. Some may finish earlier if it's just a simple device, but the typical CMOS devices usually take 2 to 3 months to complete the process flow. Okay, barulah ready to be sent to backend for dicing. Right. So any questions so far? Let's talk for about 10 minutes. Is it okay? The first part. Anything on litho? All good. Right then, so kita break sekarang pukul 10:50, 10:55. So let's come back at 5, 10, 11:05. Okay, kita jumpa 11:05. So we'll continue with second part of lithography. Right. See you then. Bye. All right, let's continue. Sekejap, eh. Problem block. Okay. Sekarang. Okay, can you see the screen? Right, good. Okay ke tu Aziz?
Ya betul?
Okay ke kat sana?
Ah, okey lah juga.
Berapa orang kat sana tu? 2 orang.
Saya Faris.
Situ ramai tak sekarang kat situ?
Ramai dah juga.
Eh,
Hmm.
line okay lah.
Hmm. Okey doktor.
Okay, harap semua okay ah. Alright, so let's move on with part 2. We're going to recap few things from part number 1. Okay, so let's go through a few of these questions briefly. So number 1, explain 8 steps in photo process. Anyone? Before we continue into the second part. What are the 8 steps?
First primer. Yes.
Okay.
Kan? Primer.
Yes.
HMDS. And then alamak, pas prime kita letak coating,
Okay. Coating guna.
photoresist.
Right, photoresist, okay.
Okay,
Next.
and then lepas photoresist kita align dengan exposure.
Belum lagi.
Kita bake dulu, soft bake dulu.
Soft bake, right? Soft bake,
Oh.
okay.
Soft bake, lepas tu baru align dengan exposure.
Okay.
Then ada bake lagi.
What is it called? The second bake?
Post exposure.
PEB, post exposure bake, PEB, okay.
Pak Faris cakap post exposure, and then lepas tu develop.
Okay, develop, then
And then lepas ada hard bake.
okay, hard bake, alright. Then
Lepas hard bake,
final
Faris
one.
cakap visual inspection.
Alright, visual inspection, okay. So those are the 8 steps, and make sure you can explain the details of each process. Right, go to the second question. What is the difference between positive and negative resist? Anyone? What is it here? Sari Izyani? Ada selingan, ha? Sebenarnya aku jawab ada selingan. Okay. So, come on, Sari. Oh, Nurul Huda, dah lama tak dengar suara. Come on. You can write down, you can unmute yourself. What is the obvious one? What is the obvious difference? Udah ke? Udah? Okay, exposure area. Okay lah, positive exposed area soluble, right? Negative resist exposed area insoluble. Okay, all right. Solubility, yeah. Okay, next. Right, what are the three types of optical lithography system? Anyone? Let's recap for 5-10 minutes and then we continue with the second one. Second part. Okay, three types. The first one is contact printing. Second one is yeah. One second one, anyone? Navina? Right, scanning projection. Yang satu lagi in between. What is it? Proximity. Okay, done. Next, what is litho resolution and how to improve it? What is resolution? R. What is R? Resolution. How do you define resolution in a simple way? Bila cakap resolution of features that you want to print, apa maksudnya? Anyone? Hadi? What is resolution, Hadi? Hadi ada jawapan? Ada dua Nur ni, siapa ni? Dua Nur ni. I go by name. Nanti you bila you log on to Webex, you guna nama sebenar. Saya tak tahu mana satu ni Nur. Ada dua Nur dekat sini. Nur saja. Okay, anyone? Yeah, resolution. What is resolution? R. Siapa tahu resolution? The resolution that you want to print or resolution that can be printed is blah blah blah. Apa maksud resolution?
Kalau saya bagi formula boleh ke doktor?
Yes, boleh.
K lambda over
Okay.
NA.
Okay, what is it? Explain sikit K lambda NA tu apa?
K process factor,
Okay,
NA numerical aperture,
okay. Lambda?
lambda wavelength yang guna untuk exposure.
Okay. So do you want our R to be high or low?
Sorry?
Do you want our R to be high or low?
Uh,
Mathematically, sebab kita the way we speak maybe opposite. Tapi based on this equation, do you want it to be low or high?
high. Saya rasa high. Saya teka high.
Okay, Razik rasa high. Anyone? Anyone think that it should be low? Amirul, high. Apa maksud high resolution? Okay, go high. Go. If we say high resolution means what? Dia kena ada clarification sikit sebab the way we speak may be different to mathematical punya description. More detail, right? So if that's the case, then apa maksud resolution then? What is resolution? Kita sebut kita nak high resolution. Generally lah, ya. TV nak high resolution, display high resolution. Tapi kalau dalam konteks lithography, how about the resolution? What do we mean by resolution? Okay, no idea. So what we mean by resolution? Yeah.
Position.
Yeah. Okay, juara tulis something. Siapa tadi cakap tadi tak dapat catch siapa tadi.
Precision.
Precision. Okay, Amiro cakap precision. Okay. Precision. Okay, Juaria said minimum feature dimension that can be transferred with high fidelity to resist. Google this. Yes, resolution is minimum feature, minimum dimension that can be printed. So that is resolution in the context of lithography. Selalu kita sebut high resolution kan. High resolution means lagi terang kan, lagi apa ni, lagi precise lah, lagi detail dia punya tu. Okay, means kalau you nak cakap high resolution, dia punya pixel size lagi tinggi lah, high resolution. But in this context, we are talking about minimum feature size that can be printed. So minimum feature size, that means we are targeting for lower R. Okay, we are targeting for lower R. Lower R means you want to print smaller CD, smaller line width. Lagi kecil lah teknologi nok tu. Okay, so that's what is meant by resolution in this case. And that's given by K lambda over NA. We're going to look into this in the second part. Okay, process factor times wavelength of illumination over numerical aperture of the lens that we use in the exposure system. Okay, so minimum feature size. Okay, next question. Yeah. Next question. What is DOF? What is DOF? What is DOF? Okay, what is DOF? Okay, depth of focus. What is depth of focus then? Do you want your depth of focus to be big or small? Yeah. Okay. Kita akan go through in this part, depth of focus. These are one of the important things. Okay, next question. Can we, this is a bit challenging. Can we directly pattern on SiO2? Pattern here, okay, you not pattern SiO2. What it means is, can we directly pattern on SiO2 without patterning on photoresist first? Why not? So what this means is you want to pattern SiO2. Kita ada SiO2 layer on resist, on silicon. Then you want to pattern SiO2. Okay, you nak pattern kan SiO2 tu jadi region yang ada SiO2 dan tak ada SiO2 lah. So that's what patterning means. Sorry. Saya draw sekali ya. So this is your silicon. This is your SiO2. Now you have got SiO2 patterns on the silicon. So the question is, can we directly pattern this without patterning on resist first? Yes or no? Possible or not? So that means you punya material to just oxide and you interact with the scanner and everything, C80%, and then you get pattern oxide. Is it possible?
Saya teka not possible.
Okay, not possible. Sebab apa? Why?
Sebab kalau kita buat directly nanti kalau ada defect apa-apa kita tak boleh betulkan dah.
Okay. Sebab you tak ada resist to be reworked lah. So that's your argument.
Yes.
Alright, okay, thank you. Any other answers? This goes back to the basic, okay? This will drills your litho basics. This question, simple je soalan ni, tapi makan dalam lah. Ya. Tapi dia very fundamental soalan ni. Nampak macam simple question, 2 line je. Okay, anyone else? Let's discuss, kita share sikit. Is it possible or not possible and why? Amiro, what do you think? Yep.
Not possible.
Not possible because Kenapa tak possible?
Oh.
Oh, you fikir dulu tu tak possible Right? Okay, let's try the Fatin. Fatin Nur Tahira, what do you think? Possible or not possible, and why? You unmute. Can write down as well. Okay, so basically the argument is same like Haziq. Okay, right? Fatin, anything? Yes or no? Possible or not? Kavina, what do you think, Kavina? Can we pattern SiO2 directly without using resist? Not sure. Okay, that's all right. Sakina? Let's have two answers to go before we discuss. Soalan last tu senang. So reward tu saya dah sebut tadi, etching plasma. Okay, Sakina, anything? Oh, Mimi. Any idea, Mimi? Syahdudu lah. Kat belakang Syahdudu lah. On, Mimi, anything? No idea, okay. Sakina, no idea. Ahadiah. Boleh tak kita patternkan SL2 without resist? No idea? Right, tak apa kita discuss. Okay, the answer is not possible. Cuma argument itu kena faham sikit. It's not possible because, okay, let's go back to the basic. Why do we use resist in lithography? Kenapa kita pakai resist? What is the special property of the photoresist that makes it irresistible? Kenapa kita kena pakai juga resist? What is the special property of the resist that forces us to use? Yep.
Dia something like dia soluble, dia protect. Saya faham macam tu lah.
Okay, alright. Any other idea? Kita kena faham tu dulu apa property resist, barulah kita boleh tahu kenapa kita nak pakai resist.
Nak buat PN junction?
PN junction, that's very indirect. Okay, tak apa. Okay, any other things? Kenapa kita pakai resist dalam litho process? It is related to the yellow room as well. Kenapa kita pakai yellow light untuk litho? Remember, photoresist is a upper sensitive polymer compound. Upper sensitive polymer compound. Blank sensitive polymer compound. That is photoresist. Light sensitive polymer compound. Okay, it is a light sensitive polymer compound that leads to reaction in certain specific region upon exposure or unexposure during the litho process that can then define the patterns. Okay, so the next question is SiO2 light sensitive? That can trigger the very same reaction? No, right? Okay, so dia tak ada, so it's not. So kalau you imagine you start off with blank SiO2, sebelum ada pattern kat sini, start blank lah, assume it's blank, cover semua. Then if you expose SiO2 in certain regions and unexposed in certain other regions without having resist on, so you will trigger nothing in the SiO2. So you will trigger no reaction at all in the SiO2, and and then as a result, bila you develop, you will be left with the whole SiO2. You'll be left with the whole SiO2, okay? Just like the way you started, because it doesn't react to any light exposure. On the other hand, kalau you ada resist on, it will Kalau dia resist on, kita recap sikit. Ya. Saya stop that. Nak dance pula. Okay, alright. Kita continue lah for the next few minutes. Semampu saya boleh. Okay. Alright, so let me just redraw this. Okay. If you want a pattern oxide, so you have to have oxide on the silicon blanket. Blanket means cover semua. Then you have your resist on. Okay. So remember, you have your resist on in order to do patterning. Okay. Without resist on, you cannot do patterning because you won't be able to define which areas to be removed and which areas to remain, and therefore that means patterning, right? That means patterning. Area mana yang ada, area mana yang nak remove. So and photoresist is a light sensitive polymer compound, so it will respond to the exposure or unexposure of the light with the right illumination wavelength. And this doesn't happen in the SiO2, so that's why you cannot do patterning on SiO2 directly, but instead you need to first pattern the resist. Setelah you remove this area, okay, so you akan tinggal area ni je. Then you can then etch the oxide, okay, and then etch the oxide. So let me buat kat atas sikit so that you understand what this means. Silicon oxide, and then kita start dengan resist that is already patterned. Okay, so this is the PR photoresist that is already patterned after CED, and then now you can see that your oxide is exposed in the central region, and this oxide can then be etched. When you etch, you can remove this oxide, and your oxide is now patterned. Okay, so remove the central oxide, then if you strip off the resist on top, you akan tinggal. Okay, if you get a silicon there, you remove the resist on top, you already pattern your oxide, you'll be left with patterned oxide. But to be able to do this, you have to go through the resist patterning first, because it is light sensitive polymer compound that will respond to the light. Okay, so is it clear? That we cannot pattern SL2 directly without resist. Is it clear? Right, good. So clear. So that's why I said it goes back to the basic. Basic here means the mechanism that is induced in the photoresist upon exposure or unexposure. Okay, so let's continue for 15 or so minutes. Okay, litho requirements. In order for you to get a good lithography quality from the patterns, there are a few parameters that you have to pay attention on. For example, the resolution we discussed briefly just now. You need to have high photoresist sensitivity to the illumination wavelength. So this is related to the wavelength of exposure, related to a positive or negative resist. Okay. Hari tu Arisha tanya positive or negative resist nak pakai kat mana. Kemudian result nampak sama kan kalau kita reverse the mask. So these are among the things. Precision alignment. So we talk about the alignment briefly just now on the plus X, minus X, plus Y, minus Y, on the theta as well. Okay. So we want to print exactly in the intended regions and avoid some of the regions as designed. And then a precise process parameters control. So for example, your CD, your defects, and some other stuff. Okay. And low defect density. Okay. So these are my requirements. Right. So let's have a look at resolution. Tadi Juharia ada bagi tadi definition. This W mean, or it can also be replaced by R. So let's look at the definition just now. Juharia tulis tadi. Minimum feature dimension that can be transferred with high fidelity to a resist film on semiconductor wafer. Okay, so the minimum feature that can be printed by a lithography process, essentially, right? So R equals to, in this case, it uses W min, tapi same thing sebenarnya. R equals to K times lambda over NA, and resolution here is equal to K1. K1 is the process factor. Process factor ni banyak benda yang masuk, macam resist quality and many other things yang terlibat dalam CAD process. So typically it's less than 1. And then lambda is the illumination wavelength. So it depends on you are using EUV or I-line or G-line or deep UV or ARF. So that will be used there as the lambda. And then numerical aperture, NA, is the function of the lens design. Okay, so lens design. Lens design dalam scanner. So NA ni dalam scanner. So dalam exposure steps, right? So 3 ways to improve resolution. If you look at this equation, if you want to go to lower R, then it's very obvious, isn't it? Kalau kita nak lower the R, so that means we need to reduce the numerator, lower the numerator, and increase the denominator, right? So that means in this case, R is K lambda of NA. So you want to reduce the product of K lambda and you want to increase NA. Okay, so therefore you have to reduce K1, reduce process factors, reduce lambda. So that's why we are moving from, say, DUV 248 to EUV 13.5. Okay, in order to print smaller features. Okay, it has print smaller features, huh? So that's the goal. Print smaller features by reducing the R. So say if you want to print, you used to print 100 nanometers, but now if you want to print 22 nanometers, so you have to move to lower lambda, okay, lower lambda exposure system. So that means new scanner lah, new scanner yang lagi mahal tu. Okay, and that's why if you relate back to the cost, previously I think the system, I think the deep UV cost somewhere around 30 to 40 million per piece. And then it's now going up to 150 to 200 million for EUV, okay? Untuk bagi lower the wavelength, because it's using different mechanism in the scanner. And then your NA has to be increased. The numerical aperture of your lens has to be increased in order to reduce the R. Okay, so that's how you increase resolution. So depth of focus is another parameter. Remember last time we talked about resist on, say you have your resist, PR. In the previous class, we talked about this central focus, and then you have plus minus. The plus minus ini is the DOF. So saya ada juga upload the PDF file about resolution and DOF on eLearn. So you can see the definition, the equation, what it means. So essentially you want a DOF to be as wide as possible. Depth of focus, maksudnya your focus will not be affected in a wide range. Okay? Maksudnya focus dia tak akan drift lah. Focus drift. Drift is another issue in litho. And focus dia tak akan drift in a wide exposure region. And then they still akan deliver the same good resolution. Okay? Kalau you punya DOF is very small, so that means you can only get a good focus with a very small region. And kalau you punya exposure system fluctuates a little bit, or resist thickness fluctuates, salah minta ABC. Okay, kalau resist you fluctuate, for example, then your DOF will be affected as well. So you want your DOF to be wide. Okay. So the same factors. You can see the description later on. Right, parameters of photoresist. There are a few parameters related to photoresist. For example, sensitivity, a measure of how much light is required in order to expose and resist. So in the millijoules per cm square. So this is the dosage needed. Dose, kadang kita sebut dose, kadang kita sebut dosage needed in order to induce reaction. Remember last time we talked about you want to make the positive resist soluble in the exposed regions. So you need to have, walaupun you buat macam tu, you still need to have a minimum dosage to be exposed. Maksudnya katalah in order for the resist to be soluble, you require 100 millijoule per cm squared, but your exposure is currently doing 80 millijoule per cm squared. So you won't have reactions in the resist then. Okay. So mana kena ada exposure dose, minimum dosage that you have to expose. So this typically comes with the photoresist specification. When you beli resist, then you're gonna know a certain minimum dosage is required for the reaction to occur. Okay. Then the next parameter is a resolution, where the effect of exposure, baking, developing should not degrade the quality of the image. Okay. So you're not thinking sharp, you want to get sharp features at the minimum size. Okay. Tak nak dia jadi apa rounded ke ataupun positive. If you want this to be printed, then you want that to be printed. You don't want something like that to be printed. Okay, this is good, this is bad. So the next parameters are chemical and physical properties. It must withstand chemical etching, mild temperature, ion implantation, and other process parameters in other process steps as well. Okay, temperature, humidity, exposure, dosage, all the stuff. So negative and positive, let's recap in the next few minutes. So in this case, you have resist sponge on your silicon, and then you have your mask or the reticle in between to allow light to penetrate through some regions. In this case, the purple arrows. So that will expose the green area. The green area is exposed. Expose. Okay, and other areas are not exposed and blocked by the chrome on the mask. Okay, so if it's on negative resist, so the exposed area will be hardened. So after development, after the D, remember CED. So after the development, where you want to see your features, if you use a negative resist, then you're going to have these features because the exposed areas are hardened and left behind on the silicon. On the other hand, if you use positive resist, the exposed areas, same areas will be removed. And you'll be left with the unexposed areas because your exposed areas are now soluble during the development process. Right, resist composition. They are in the resist, there are a few things. Dalam photoresist, dalam tu ada polymer, solvents, that's why you need to drive off the solvent during the hot plate process. Sensitizers, additives, they're all in the resist. Right, it's a solid organic material, light sensitive. Okay, it's a light sensitive polymer compound. Transfers design pattern to the wafer surface, so it will transfer the circuit on the reticle to the wafer. It will change solubility due to photochemical reaction upon exposure or non-exposure. Okay, solubility will be changed depending on positive or negative. A positive PR from insoluble to soluble. If you're talking about exposed area, need to expose area, yeah. On the other hand, if you talk about negative resist, also to the exposed area from soluble be insoluble, it will harden. Okay. Solvent in the resist, dissolve polymer into liquid, so it makes it liquid resist. Allows application of thin resist by spinning. Kalau tidak susah, kalau you nak spin coat a very thin layer without solvent, then it's going to be very viscous. Resist is very viscous, dia pekat. So kena ada solvent bagi dilute sikit so that you can spin more easily, right? 75% of photoresist before spin coating, this is the composition of the solvent, and these are the solvent type that's used. Acetate type for positive resist, and xylene for negative resist. Xylene is C8H10. Sensitizers control and modifies a photochemical reaction during exposure, determine exposure time and intensity. So bila kita beli the resist tu, there's gonna be SDS for the resist, and then there ada resist punya technical spec, resist technical spec. So you beli apa pun, you're going to have these technical specs. So it will tell you the minimum exposure dose, time, intensity. Even other vendor yang akan advise you, those who sell you the resist. Okay. Then additive, various added chemical to achieve desired process results, such as dyes and to reduce reflection. Okay, you don't want to have reflection because there'll be an issue. Okay, resist a silicon, photoresist. You're gonna have some reflection due to interfacial reflection at the resist surface interface. Air resist interface is one interface, and then resist oxide, belakang ada oxide, resist oxide is another interface. So that will give you some level of reflection, and this reflection will appear on the features of your resist as a standing wave. Kita akan tengok nanti ya. Bila you ada reflection, then you want to print this. But you will end up with this. So you got, but then it's going to be some ridges on the profile. Ini bentuk wave dia punya ni sinusoid sinusoidal shape. So it's actually due to reflection of the light during the exposure. Dia akan replicate the wave punya shape tu dekat vertical feature. So you're going to have like standing wave effect. We call that a standing wave effect. We're going to learn that later on. Negative resist, most negative resists are polyisoprene type. This is the polymer. Okay, exposed resist become cross-link polymer. Okay, cross-link polymerization. That's why it hardens, but dia lagi kuat. Cross-link polymer has higher chemical etch resistance. That's why when you develop, dia tak akan remove sebab dia ada higher chemical etch resistance due to cross-linking atau cross-polymerization. So that's why for the negative resist, when you expose, it will be hardened and left there. So it will be able to withstand the higher resistance of the etching. In this case, the timah. Unexposed part will be dissolved in the development solution. Right. Okay. Negative resist. I need just the repetition of the slide is now. The exposed areas are not removed. Okay. So this is the cross-link polymerization, the hardening, and therefore higher etch resistance. Cross-link polymerization, right? Disadvantages of negative resist: the polymer absorb the development solvent, poor resolution due to PR swelling. Resist ni boleh swelling, dia boleh membengkak. Dia boleh membengkak in some condition. So, okay. Environmental and safety issue due to main solvent xylene, right? There's always environmental issues related to the fab because fabs contain all the dangerous chemicals and gases as well. So always pose environmental and safety issues to the staff and the environment. Okay, you can see here the swelling. Dia kembang ke tepi tu. So this is the swelling. That's not commonly seen on positive PR, even though positive PR ni tak adalah macam exactly straight, dia positive sikit lah. It's a bit like that in real case, but it won't be as bad as negative. But there's a way to manage that, right? Positive resist, exposed part dissolved in the developer solution. We discussed this one a couple of times. Image the same that on the mask. Yep, we want to print exactly the same circuits on the mask. Higher resolution, commonly used in advanced IC fabs. Right, CA resist is what you use on DUV, so it's called chemically amplified, and DUV uses 248 nanometer. To pattern a small feature, shorter wavelength light source required. For this case, it can be 248 or 183. Okay, light source excimer lasers. So for 248, we use KRF, krypton fluoride. For 183, we use ARF, argon fluoride. So different sources to generate the lasers. Light intensity is lower than I line if you compare DUV to I line and J line. So we need specific type of photoresist. So this CA resist, catalysis effect is used to increase effectiveness of resistivity. So we discussed this briefly when we talk. So we'll induce reaction in the DUV resist. Okay, photoactive acid generator is created in the PR when it is exposed to the DUV light. We call that SPAG, photoactive acid generator. Okay, PAG. There's some details, right? During the PEB, head-induced acid diffusion, the acid diffusion causes amplification in the catalytic reaction. Acid remove protection group, exposed part will eventually be removed, but it will ensure the quality of the patterns that we print after the DUV process. Right, other requirement, high resolution, thinner PR has high resolution, okay, high edge resistance, good addition, wider process latitude ni, in other words, is process window. Bila you masuk fab ataupun mana-mana industri, normally kalau you process engineer, we will be talking a lot on this, process window. Process window tu means how wide can you run the process without affecting the quality of the final devices. Maknanya kalau dia boleh across certain parameters, for example, focus and dose, kalau you boleh run a wide focus and dose without changing the quality of the CD, for example, then that means your process has a wide process window. Maknanya you ada margin for error lah. Kalau let's say you focus drift, scanner and focus drift, it won't affect the CD as much. So that means you have a very wide process window. On the other hand, if you have a very narrow process window, a slight drift in the scanner punya drift focus ataupun thickness of the resist will change the CD significantly. So in that case, you have a very narrow process window. So wide process window allows a wider fluctuation of the process. So that means your process can afford to fluctuate without giving detrimental effect in final devices. However, if you have a very short or narrow process window, you can't afford to have variation as much as the wide process window. So slight variation pun, it will alter the CD significantly and that will affect the next processes. Okay, so we aim for a very wide process latitude or wide process window. Contoh kalau saya ambil parameter X and Y, contoh je, just any parameter. Then you measure your CD, CD. Okay, so that is case number 1. So case number 1, this is your CD. Case number 2, this is your CD. So case number 1 or case number 2 has a wide process window. Process number 1 or process number 2 yang ada wide process window. Look at the general plot there, just to illustrate to you the meaning. Okay, 1, kenapa Amirul? Kenapa 1? Kenapa 1 has a wide process window? Why are you saying 1?
Sebab range dia.
Range apa? Explain sikit.
Like, area dia lagi besar.
Okay, and does the CD change at all?
No.
Look at the line. Does the CD change at all? CD untuk case number 1, does it change at all? If you change your Y, for example, do you get any change in your CD?
No.
No, right? So maksudnya bila, for example, katalah Y ni you punya one of the parameter dalam CED. So maksudnya kalau you punya Y ni fluctuating within this, your CD won't change. Your CD ni fixed. On the other hand, if you go for process number 2, kalau you punya Y ni fluctuate sikit, you punya CD will change, right? Dia akan change from one point to another point. So then kalau fluctuate lagi, dia akan naik ke situ, dia akan naik lagi tinggi. Kalau fluctuate within this region, then dia akan berubah this much. So your CD will change a lot. Then you pergi lagi tinggi, Y ni dia turun pula. So it's not stable. Maksudnya you really have to control your process so that you can manage the fluctuation. Okay. On the other hand, kalau proses number 1 tadi, pertama tadi, you can have a privilege of having fluctuation without affecting the CD. Maknanya CD akan remains fixed. Okay. So in this case, process number 1 yang ada wider process latitude or wider process window. Dan dia boleh bernampah lah, dia boleh ada some error, ada margin. Sebab bila you ada process equipment, dia akan ada fluctuation. But the fluctuation is natural lah. Dia akan ada within its natural window. Dia akan fluctuate sikit tapi yang okay punya lah. Bukanlah macam very wild. Okay, kalau very wild tu means something is wrong somewhere lah in the process or in the equipment. But then kalau proses yang okay pun, yang stable pun dalam fab, normally it will have some natural fluctuation that we will see every day. Okay, so and this natural fluctuation has to be kept within a wide window as the best case. Maknanya kita nak kalau boleh kita ada wide window yang fluctuate tapi dia tak affect the final result. Okay, and that's called wide process window. Kalau narrow process window fluctuate sikit pun dia dah kacau kita punya result lah. Then you have to control the parameters very strictly so that you don't affect the results. For example, these parameters that you have to control can be spin coating rate, hot plate temperature, tolerance, exposure flux in terms of dosage and focus. Sebab kadang-kadang dosage and focus dia boleh drift dalam scanner. They will drift to a certain extent. They can drift to a certain way in some condition. Okay. Kadang-kadang you can predict, kadang-kadang you cannot predict. Okay, so that's why the PM comes in, the preventive maintenance, to make sure that everything is in control. Okay, so you want to make sure that this is achievable. Okay. Okay, resist performance onward, I'll discuss in our next class on Monday. Right? Is it okay so far? We'll try to finish the remaining parts on Monday, and then we'll move on to etching on Tuesday. Right? Any questions so far on part 2? Okay,
Doktor,
Yep.
sebenarnya saya tak faham sangat yang graf yang doktor tunjuk tadi, yang CD tadi. Saya tak
Oh,
faham sangat.
okay. Right. Mana tadi? Oh, saya pergi discard pula. Which page tadi? Chemically amplified, resist properties. Sini ya. Okay, tak apa, saya just draw je lah. Saya sketch balik. Hold on. Okay. You can see the slide, right?
Yes.
Katalah you ada factor X and Y. Nanti kita akan belajar benda ni ya. Saya sebut dulu. Then factors that you want to control, for example, and then you measuring your CD. This is your first process. This CD result, it can be like points on this line lah, for example. Then on the other side, process number 2 has this kind of shape in the CD, a dome shape lah.
CD tu apa ya doktor? Saya tak fokus.
Okay, right. So let's go back to that. CD is the critical dimension or line width that you want to print. Okay. So remember the resist pattern that yang kita print on the silicon. So the width of that. So it goes back either you print the line or the hole. Okay. Line atau hole. Tapi in this case kata you print lines. So this will be the CD, the line width of your patterns. Maksudnya kalau you print atas silicon, then you'll probably be printing like that. So this is the CD of each. CD ni is determined by the line width of the patterns on the reticle. Kita ambil mask, kita nak print feature yang sama kan, exactly on the wafer kan. And you want to print that and you know the exact dimension of this line. For example, line ni panjang ni, on the reticle is this much, and then on the wafer bila you print on the resist, katalah you reduce 5 to 1, then maybe it's 500 on the reticle, 500 nanometer, and then it's supposed to be 100 on the resist. So that means bila you print, you're supposed to get 100 nanometer of your resist punya line width on the pattern. But then you won't be getting that in some condition. Okay. So katalah proses pertama you vary parameter dalam you punya scanner, for example, you always get 100. It's not changing at all. On the other hand, if you change the very same parameter in the scanner using process number 2, then you will see that the CD fluctuates. Mula-mula dia say 50, 70 contoh. Then you change sikit, dia naik ke 80, naik ke 90, then tiba-tiba naik ke 120. Then dia reduce balik ke 70. Kalau you keep increasing factor Y, for example. Contoh ya. So in this case, the question was, which process is more stable? Which process has a wider process window? So the answer would be process number 1, because despite the fluctuation of the parameter y in this case, the CD remains unchanged ataupun minimal change. Mungkin gradient is very small, close to 0. On the other hand, if you use process number 2, kalau you tukar y sikit ataupun y fluctuating sikit, yang you tak tukar pun, you tak control tapi dia fluctuating, then the CD is already on the rise, isn't it? Kalau you tukar y, you increase y daripada kiri ke kanan sikit, there to there, you can already see the change in CD, for example. Maknanya, upon a small fluctuation of the system, the CD already changed. Maksudnya, you punya process window is not wide, it's very narrow. Maknanya, you kena control you punya parameter tu very strictly so that your CD doesn't drift. Okay. Kadang-kadang fokus dalam scanner drift, CD will drift. Dosage drift, CD drift. Thickness of photoresist drift, CD drift. Kadang-kadang flow rate of developer dispense drift, CD drift. Then what else? Banyak lagi lah faktor yang ada. PEB, temperature drift, CD drift. Hot plate, hard bake, temperature drift, CD drift. These are among the things that I'm talking about. The factors could be, the Y here could be dosage, focus, hot plate temperature, positioning of the robot arm, for example, developer flow rate, resist dispense flow rate, and the spinning speed, cool plate, thousands of different factors dalam CD process tu yang could cause your CD to drift. And you want to know the process window, okay? Kalau process window tu wide, that means you ada fluctuation sikit-sikit pun, tolerable fluctuation, the CD won't drift. On the other hand, if it's a narrow process window ataupun narrow process latitude, drift sikit pun CD dah drift lah. Drift sikit, alignment dah drift. Drift sikit, then you punya defect, ada issue ke apa, something like that, right? So the process window tu is a very general term for me to show that a stable process has a wide window, wide fluctuation, wide apa ni, you can't afford to have fluctuation of your factors. On the other hand, kalau very narrow, then sikit change je, dah habis. You can off. Is it okay? Is it clear?
Yes.
Okay. So, yep.
Maksudnya CD ni dia hanya affect photoresist ke? Maksudnya
Tak. Photoresist is only one of the factors that could affect the CD. Tapi banyak lagi. Scanner dose, focus, developer, hot plate, cool plate, robot arm positioning, resist expiry date, EBH, HMDS expiry date, banyak benda. So bila you ada, for example, kalau you ada satu isu CD drift, you cannot really pinpoint the top 2-3 factors. It really depends on the nature of the problem. Contoh macam tadi CD drift, tapi kita tengok tadi wafer one sided kan, yang problem waktu hot plate slanted kan. One sided okay, tapi 50% lagi tak okay. Then it's very unique lah. CD drift juga in this case. One side CD okay, one side CD tak okay. Drift tu means it's running way off target. Kalau you target 100 nanometer plus minus 3 nanometer, then suddenly you punya CD gets to be 105 ataupun 96. Kalau 100 nanometer target plus minus 3 nanometer, so that means your CD can only fluctuate between 97 to 103 to be considered okay in spec. Kalau you tengok tiba-tiba 96 which is on the lower side or 105 which is on the higher side, dah terlepas pun keluar pada spec, something is happening. So we call that as CD drift. Okay, and this CD drift can be in the form of many problems. Okay, contoh the whole wafer drift ataupun satu section je drift ataupun 50% je drift. Then this problem in its own way will lead you to different root causes. Okay, macam ni kalau 50% je, then slanted punya issue. Kalau the whole drift, then maybe dosage drift ke, atau focus ada problem ke, ataupun resist thickness memang tak cukup ke, ataupun terlebih ke, ataupun resist tiba-tiba expired ke, terlupa nak ganti ke, technician lupa nak replace the new photoresist ke. So it could be due to thousands of different root causes. Okay, tapi dia punya issue dia CD drift. Cuma bila nak troubleshoot nanti, you have to really go down really have to understand the problem. CD drift ni macam mana, what is, how much does it drift? How is it like? Kalau you cakap CD drift, kan you punya buah akan tanya, so how much does it drift? How does it drift? Why does it drift? Kan? Do you see any patterns or not? Is it systematic? Systematic means ada sebab, ada pattern, atau is it random? Is it coming back? Will it come back to the center? Kalau tiba-tiba hari ni dia 103 nanometer, tomorrow will it come back to 101? Or it will just drift to 105 and 107, 108, 109. So banyak benda lah kat situ, maksudnya dari segi operation, working as the engineer for lithography ni, dia it can be thousands of different issues. Okay, tapi the essence I would like to tell you is process window. Itu yang paling fundamental you nak belajar sekarang. Tapi bila when it comes to the real CD drift problem ni, dia akan jadi banyak sangat benda. It can be the process, can be specific module, it can be the whole thing, it can be scanner plus track, it can be just track. So bila you troubleshoot tu, you akan rule out one by one sampai lah you jumpa the cause. So that's how it works as a process engineer or equipment engineer in wafer fab. Right? Okay, clear? Any question? Belah?
Clear, Doktor. Thank you.
Right, good. Then I'll see you next week, Monday, inshallah. Okay? Bye-bye, take care. Assalamualaikum.